In this unit, we're going to bring together what we've learned so far and finally obtain a simple expression for the sound speed. Then we're going to consider what happens when we have a sound source that moves. Sound waves are infinitesimally weak pressure waves. By applying conservation of mass and momentum to such a wave, we found out that the sound speed squared is equal to the derivative of pressure with respect to density at constant entropy. For an isentropic process in a thermally perfect gas, we use the first and second laws of thermodynamics to show that the pressure P is equal to a constant C times the density ρ to the power of the ratio of specific heats, gamma. Note that we can also rearrange this to obtain the fact that the constant C is equal to P on ρ to the gamma. Let's take the derivative of this expression for P to find the sound speed. A squared is del C ρ to the gamma del ρ. And that's going to be equal to gamma C times ρ to the gamma minus 1. Making use of our expression for the constant C, we can simplify this to obtain gamma P over ρ. Taking the square root of this, we finally obtain a simple expression for the sound speed. A equals the square root of gamma P on ρ, or making use of the ideal gas law, the square root of gamma RT. Let's use this expression to answer the question: how fast does sound travel through the air that you're breathing right now? Well, for air, the ratio of specific heats gamma is 1.4, and the gas constant R is 287 joules per kilogram Kelvin. In the room where I'm sitting, the temperature is 25 degrees Celsius or 298 Kelvin. You may need to modify this calculation for your local temperature. Using this data, the sound speed is given by the square root of 1.4 times 287 times 298, which is equal to 346 meters per second. This means that it takes sound only 5.8 milliseconds to travel the 2 meter distance from me to the camera. The sound speed can be quite different in other gases. For example, room temperature helium, which has a gamma of 5/3 and R equals 2077, has a speed of sound of 1016 meters per second, almost 3 times higher than that of air. Next, let's look at what happens when a moving object, such as a car or a jet, emits sound waves. Depending on the Mach number with which the object is moving, we're going to get very different results. We're going to examine when an object is moving with a constant velocity v through stationary air that regularly emits sound pulses at regular intervals in time. First, let's look at the sound waves when an object is moving at subsonic speed. As the object, represented by the red circle, moves to the right, so does the origin of the waves it emits. This results in the wavefronts being much closer together on the right. As a result, if you were to listen to this sound, it would have a higher frequency than the sound on the left. This is the Doppler effect. Next, let's examine what happens when an object moves at exactly the speed of sound. In its direction of travel, the object now keeps up with the sound waves it's emitted. This means that if you're in front of the object, you can't hear it, as no sound waves are propagating ahead of the object to warn you of its coming. Once the object passes you, however, you'll encounter the intensified sound that's built up at the front of the object. Finally, let's examine what happens when an object is moving supersonically. The object now outruns all the sound waves it generates, leaving them behind in its wake. If you look carefully, you can see that the sound waves are all contained in a cone behind the object. This is known as the Mach cone. We can easily compute the angles of the sides of the Mach cone using simple geometry. In a time interval delta t, the object travels v delta t to the right, while the sound wave will propagate a delta t outwards from the point where the object started. If we complete the triangle, mu is the angle of the cone from the path of the object. From trigonometry, sine mu is equal to A delta t on V delta t. If we cancel out those delta t's, this is just going to be equal to 1 on the Mach number. Thus, mu is equal to the inverse sine of 1 on the Mach number. This is known as the Mach angle, and it defines the geometry of the Mach cone. You can only hear a supersonic vehicle within the Mach cone, as this is where all the sound waves are present. Hence, it's also known as the zone of action. Outside of the Mach cone is known as the zone of silence for obvious reasons. This implies that you can only hear a supersonic object after it's already passed your location, which you can experience firsthand if you witness a supersonic jet flyby.